So today it's my pleasure to have Xuefeng, who will be speaking about solution verification for the stationary Navier-Stokes equation over bounded non-convex 3D domains.
Okay, many thanks for the introduction from Jean-Philippe. Glad to meet everybody online. I hope to visit you in your future, not online. Okay, so this day I would like to give a talk. So on the solution verification for the the stationary Navier-Stokes equation. So it is for the moment just the limitation to stationary solution. So over bounded non-convex domain. Yes, convex and non-convex domain. So okay, so this work is cooperated with Professor Nakao and Professor Oishi, an idea for many people, many friends. I will introduce in the slide. Come on. Okay, so okay, the outline. So very short introduction to the Navier-Stokes equation because I think everybody know the basic thing about this equation. And then the main theorem for the solution verification and some problems, some numerical result and to-do problems. So okay. So Navier-Stokes equation. So it describes the moment of fluids, the air, the water. So for example, the sea at Niigata, the first picture here, okay, is nearby our campus. And the second picture is from Wikipedia. It's about the protect a cloud after airplane. So, okay, the history for the Navier-Stokes equation, just review. So in 1922, Navier proposed the formulation for viscosity fluid. And then later, about 30 years later, so Stokes, S.G. Stokes, so generalized the equation for the fluid. So now we call this equation the Navier-Stokes equation. Okay, okay, just a very short and fast review of the equation. So they are very various settings to set up the model of the moment of fluid. So here we are considering the incompressible fluid. So you see there are velocity, pressure, body force, viscosity coefficient epsilon. So and also the boundary condition. So in our you see a computer assisted proof. So for the moment we are considering the homogeneous discrete boundary condition. So there's some result, known result and unknown result about the NS equation. This is with many people have interest in this problem. So for the 2D case, so the Navier-Stokes problem in some sense has been solved by Lili-Jinskaya. So there exists smooth and globally defined solutions. But for 3D, so there's some result, yes, but just under some special conditions. So under such kind of assumption, we can have some result, something like that. And also we can apply the numerical scheme to find some approximate solution. So, but you see, for the numerical solution, there are some instability and also error. So it is very hard to draw reliable conclusions. So this is cited from the official problem described by the Mathematical Institute. So we can do numerical computation, but what kind of information can we have from the numerical result? So this the talk is about the solution verification for stationary solution. So let's cite some known result. So from theoretical part. So from the book of Dirac and Rabiot, so there's the theorem named number 2.2. So okay, the function space divergence-free with homogeneous discrete boundary condition. If we define quantity n and also the norm of f, so if the condition, so there okay in the middle place there, this condition, so it holds, then the Navier-Stokes equation has a unique stationary solution in this function space. This is some theoretical result. So in some sense, so this result is a little raw because for smaller epsilon, then the value, let me try. yes, this one can be bigger. So this is the raw estimation. So our aim for the moment is just to do some computer-assisted proof that you see even for larger epsilon and complex domain. So we want to show some proof for the solution existence. And also we want to tell people that okay, the approximate solution is something like this, and the exact solution is nearby this approximate solution. So this theorem is just the solution exists, but give no information about what it will be like. Oh, didn't work there. So yes, the solution verification by computer-assisted proof. There are some basic concepts. Although I think it is well known for the people here. That's a short review. So thanks to this IEEE 754 standard, so it defines how to do the floating point number operation. So there are 4 rounding modes. So by switching the rounding mode, we can have exact lower bound and upper bound for some expression. For example, 1 or 3, we have lower bound at 1.33 and upper bound at 0.34. So the lower bound, upper bound are exact. So, and also we can introduce the interval, and we can do the computing with interval unit. So also, we can further apply such idea to the the linear problem. So the algebra problem like so ax equals b is a linear equation, ax equals lambda bx. So to have rigorous result, so we need to develop something totally new idea and a new algorithm to have the rigorous result. So here. So I will skip the detail about for example, how to solve the linear equation exactly. So there are many people working on this subject, so we can use the result from the people in this field. So let's shift to the main theorem about the solution verification. So it is about the fixed point theorem. So yes, the fundamental theorem or the fundamental tool is the fixed point theorem. Fixed point theorem. So okay, let's consider a very simple case in 2D case. So we call broader fixed point theorem. So let T be a continuous mapping on closed disk. So here that's the plane. Yes, if TD belong to D, then T has a fixed point in D. So this very simple fixed point theorem. So there are many variations of the fixed point theorem. Upon selection of D and T for infinite dimensional space, the shorter fixed point theorem is needed. So okay, this was the basic thing. So in a computer-assisted proof, so for concrete D with approximate solution at the center, so we want to verify that TD belongs to D. So this is the abstract set, but we want to show the relation between each other. So and then by using the some fixed point theorem, we can declare solution existence. Okay, so let's go back to the Navier-Stokes equation and reformulate at some some equation with functionals. So over a bounded 3D domain, here we consider 3D. 2D can be regarded as a special case in 2D, but the FEM space and the mesh generalization is little different. So in this talk, we just focus on 3D. So the equation has epsilon and also the you see the pressure terms and the convection terms and so divergence U, divergence-free condition for U, and on boundary it is 0. So we can define the equation of function nodes. So the function space, so V, it is a divergence-free space. So this is a little special thing in this talk or in this research. So throughout all the discussion, so and also the computation, we want to implement some divergence-free space or subspace. So, and then we construct some error estimation and a fixed point theorem. Yes. So, Okay, so we start at the dual space of V. We can define operator A and N. So in this form. Okay, we can define F equal A minus N, and the Navier-Stokes equation becomes some FU equals 0. The equation is very simple, but yes, it involves several operators inside. So okay, let's review the Newton method. This is just for 1D case. Okay, for a basic thing. So we do the Newton iteration, then we can have a sequence of approximate solution that converge to the exact solution. So this is the start point, and we want to use this Newton iteration and also some fixed point theorem related to this method. So here is the yes. So okay, for Navier-Stokes equation, we solve the equation by using the finite element method along with the Newton method. So we will first construct our approximate solution by Newton method, and then we want to verify that nearby this approximate solution there exists some exact one. So here is the theorem. So we are using it is called the Newton-Kantorovich theorem. So let's get familiar with the notation here. So f dash u hat. So u hat is an approximate solution, okay, by some method, for example, Newton method. So f dash u hat be the fresh derivative of f at u hat. So yes, so we assume that okay, this one is regular, and following equality holds with some constant alpha. So yes, already in red. So yes, the alpha quantity is very important. Later, we want to give concrete value for this quantity. And let this bu hat to alpha. So it is closed ball center at u hat, and the radius being 2 alpha. So, and also we consider something about the continuous. So so below there, here is the inequality. So for the function in open ball D, so it's something like this. So there comes the omega, constant omega. So later we also need the concrete value of this quantity. So basically, if we want to apply the Newton-Kantorovich theorem, we need the two quantity. And yes, if this condition holds, then we can declare that this equation Fu has a unique solution in this ball. So with the radius rho, something like this. So okay, clear screen. Yes, nice. So from 1990s, so Bloom, Oish, and Nakao. Maybe not the order like this. Okay, just in my slide, order like this. So consider solution verification method based on the fixed point theorem. And so in my opinion, and so the above mentioned fixed point theorem, so they developed some fixed point theorem or applied some fixed point theorem to discuss to investigate the solution existence. In my opinion, so these fixed point theorem are essentially the same to the Newton-Kantorovich theorem, and they are sharing the similar subproblem in practical implementation. So there are different approach. If we want to apply such approach to give solution verification, so we have to solve some common problem. So here I list the problem here. So now we summarize the quantity by three. So first, so it is about the norm estimation for the inverse of the operator. This fresh derivative of f. So okay, so there are some quantity. Okay, yes, and also for the approximate solution, you had the residue error delta. Okay. And also something about the local continuity. So this is G. So with K in delta and G, we can give the value for the alpha and omega in the Newton-Kantorovich theorem. So about among these quantities, so the estimation of K is the most challenging problem, the most difficult thing. So this K. And for other quantity is okay. We can obtain some upper bound and also sharp upper bound. So also here the G for the valuation of G, we have to solve some eigenvalue problem for the Laplace operator or Stokes operator. I will show it later. So,
Xuefeng?
Yeah.
I have a question. Can you go back to the previous slide, please?
Oh, please, yeah.
So for the constant G, I mean, the fact is that you compute the Frischia derivative on the left, and the Laplace operator in your equation is that's part of the linear part, isn't it?
You see, I
guess I don't understand why. I guess I don't understand why the G depends on the Laplace operator, because if you take the Frischia derivative and then you take the difference, the linear part should vanish, or not?
This is not related to the linearized operator. So this just about the Poincaré constant.
Okay.
Poincaré constant. Yeah.
Oh, I see. Okay. Yeah.
It just can help us to improve the estimation. Not so essential, because we can also have the upper bound for Poincaré constant by other theoretical result. So.
Okay. Thank you.
So generally, the evaluation, okay, so we have considered some eigenvalue problem of the differential operator. So it is about a non-self-adjoint operator, and it is really difficult to solve. So here, we avoid the problem to solve the eigenvalue problem there. So we turn to the method of Nakao. So the theorem developed around 1999, and also there's one application on Nakao method in a paper you see a quarter with Tagayasu and Oishi in 2013. So if we want to apply the method of Nakao, we have to give the priori error estimation for the FEM solution to the, okay, this is Stokes equation. We can regard this one as the linearized equation or the Navier-Stokes equation. So for this is linear equation. So we need the a priori estimation for the FEM solution. We can apply FEM to obtain some approximate solution, but we need some so a priori estimation that hold for all F. So yes. So this is the theorem developed by Nakao. This in the formulation is the so in the paper in 2005. So there are several things. So let's check it. So you can see there's a PH. So PH is the projection operator from the divergence-free original space to FEM space. So FEM space is also divergence-free, the projection operator, so PH. And for other operator, so I think I explained already. Yes. And so in this theorem, so there are several quantities, nu1 and nu2 and nu3, and also some quantity tau. And this theorem give some estimation for the for this quantity. Yes, this is this is just the upper bound. So we can, this bound, upper bound can be denoted by K. So in this theorem, the most important or difficult thing is about the evaluation of tau. So in the numerical computation, we paid too much effort. Yes, that's to have explicit value of this tau. And also to give the value of tau, we need the prior estimation for the projection operator. So in 1998, so for 2D starship domain, Nakao and his group with Yamamoto and Watanabe, so they applied the Hogan result about the bound CH in the prior estimation. So the solution verification for general 2D or 3D domain are very difficult. So let's check. So what can the wait a moment. Okay, the figure it is paired. Okay, I'm sorry. Okay. So in this talk or in my recent research, we are considering for general 2D domain, not limited to starship domain, and also for 3D domain. For 3D domain, even for cube domain, there's no report for the solution verification. Okay, let's go to the subproblems about application of the Newton-Kantorovich theorem. So basically, two problems. So one or the most essential problem is about a power error estimation for the projection pitch. So it is required by K. So the challenge is that the 3D domain and also domain can be non-convex, and also there exists the divergence-free condition. So there are many constants, for example, the Poincare constant, and then we needed to solve some eigenvalue problem. So some eigenvalue problem of Laplace operator or Stokes operator. So basically, it's not so easy to obtain lower bound for the eigenvalue. So recently, in my work, so I developed a frame to give the lower bound for general self-joint differential operator. So now, to have some lower bound for the eigenvalue problem, so it's not so difficult. So I will show some example in this slide. Okay, let's consider the prior estimation for the projection pitch. So now we consider the linearized equation. We call it the Stokes equation. So it's a linear system. So we also divergence-free space. And VH is conforming FEM space. So conform means you see, although it is a finite discretized space, so all the element function is divergence-free. Basically, this is not so easy to construct. So we applied the so-called the Scott-Wojcicki FEM to implement such kind of space. And the space is not explicitly defined. So it is defined by utilizing some constant condition. So I will explain it later. So here, there's some problem that in the computation also. The projection pitch, okay, very simple. Just you see by the inner product. So okay, defined in this way. So we need the prior estimation. So in this form. So with the energy norm. So the difference between U and projecting U is bounded by L norm of F multiplied by some constant or quantity CH. So basically, quantity CH will tend to 0 at mesh size tend to 0. So it is so difficult to explain the projection for the Stokes equation and directly. Let's just review some basic results about Poisson equation. The Poisson equation is very simple. You just get a function, and it's okay. There's a model problem in many textbooks. So Laplace U okay equal F in omega, and is 0 on the boundary. So in case convex domain. So for example, we have triangulation mesh with the right triangles. Then we can give the a priori estimation. So with quantity like this. So very beautiful inequality and very beautiful numbers. But this holds just for convex domain and right triangles. Yes. So in early days, Yamamoto and Nakao verified that the value some constant named the Babska constant in this range. So very sharp. And later, with my supervisor, Professor Kikuchi, so we proved that you see the Babska as this constant. So it is the root of transcendental equation. So we can easily calculate that C has value like this. So and later, so in my work and also the work of Kobayashi, we developed formula so to give a bound, upper bound for the constant for general triangle element. So this one here, that this number that's for right triangle, but also we have result for general shapes. For non-convex domain, because solution may be singular, so U does not belong to H2 anymore, then the prior estimation is very difficult. And also, Yamamoto Nakao in 1993, he proposed method to estimate CH. So for L-shaped domain, where domain is extended to be a square domain. So, and Kobayashi also developed some method to give this prior error estimation for 2D non-convex domain by utilizing some singular bit function. So it's a little complicated. Anyway, it works. So with Professor Oishi, so we developed a prior estimation based on the hypercircle method. So this hypercircle method is very interesting, very useful, and it can easily deal with domain with general shape in 2D or 3D, or and also not limited to the some homogeneous boundary condition. It can be some mixed boundary condition, directly boundary condition, non-human boundary condition, no problem. So it is very useful and can solve many kind of problem. So okay, let's just review the hypercircle method. So let U be the solution of Poisson equation. Here we just focus on the Poisson equation. So U is the exact solution. We take P from each diff space. So P is not unique. It satisfies this condition. There are so many P that satisfy this equation, and also we have something like test function V from each one zero space. It can be arbitrary one. And then we have the following equation hold. So this we call it the hypercircle or Pythagoras equation. So because you see the three quantity that form a right triangle. So U is unknown, it is exact solution unknown, but P and V is computable. We can construct concrete P and V in some sense. And then by using the value on the right hand side, we can give upper bound for this term usually the error term. Okay, for example, V is approximate solution and U the exact one. So U is unknown. We have no information directly, but we have upper bound from the one on the right hand side. So this idea works well for Poisson equation, and also it works well for the Stokes equation. Okay, now So here is a short history about the hyper method. So just one point here. So in Japan, so Professor Fujita in early days in 1955, he considered a boundary value problem in the form T star TU equal F. And this can be regarded as an extension of the work Kato. And their method, so essentially the same thing as the hypercircle method. So here I quoted some sentence from the paper. So it is not essentially different from those proposed by the author hypercircle method. Okay, very interesting. In this case, I applied the first result directly to obtain some other interesting result. Okay, so here, so Kikuchi, my supervisor, so he applied the hypercircle method to develop the posterior error estimation. So, and I introduced just now, so with Professor Oishi, we developed the prior error estimation for domain or general shapes. Okay. So now we can do the Stokes equation. So the Proton equation, in some sense, it is well done, but for the Stokes equation. So for the divergence-free condition, so there's some well-known theorem named the Babs-Gardet theorem. So this theorem helped us to set up the relation between, you see, the gradient U and the divergence of V. Okay, gradient V and the divergence V. So if the approximate solution is not divergence-free, so the Q is not zero, there's some related error, we can apply this inequality to give bound for gradient U, and then we can apply this one for the proof. But unfortunately, in this inequality, the quantity, inverse of beta or beta itself is very difficult to obtain. So for Starship 2D domain, so Hogan provided some explicit bound for beta, and the Nakao group developed a prior estimation by using this result. So unfortunately, it's very difficult to obtain such kind of beta for general 2D domain and for 3D domain. This is a bottleneck problem. Okay, here is the graph. So this is Starship. So on the left side, it is the Starship domain. On the right side one is not a Starship domain. So okay, so now we applied hypercircle method for Stokes equation. So okay, U be the exact solution of the Stokes equation, and also we have P from HD space. Now P is okay. The condition for P is a little complex. So the divergence P plus gradient of some function and plus F is 0. So and for any function V, arbitrary one in this divergence-free space, we have the hypercircle like this. So very beautiful, very beautiful. Also, on the right-hand side, P and V, in some sense, it's computable. We can have explicit form. We can construct it directly. So yes, in FEM implementation of this hypercircle, so we need the Scott-Wojcicki FEM space, and the P from the Rabier-Thomas FEM space. So also here, the idea of utilizing its phi comes from Bloom. So when I discussed with him about eigenvalue problem, he showed me the idea. So we need a phi like this. Without phi, we cannot have good bound estimation. So yes, the phi is very important. Later, we realized that the phi is something like the pressure term. So yes, in the Stokes equation, there's the pressure term. So the gradient phi is necessary. So this phi we don't need to. In some sense, it can be determined automatically. So we don't need to pay effort to find a concrete phi. We just solve some set point problem, and the phi will come automatically. So okay, so here is a prior estimation for Stokes equation. So there's the quantity kappa h. So it is defined over xh. Xh is some piecewise polynomial function. There's no condition about continuity. So it's totally discontinuous function. And pH, HD function that satisfies the side condition. So in previous page, and VH just it is some FEM space divergence-free, and all the function space here are finite dimensional space. So we can evaluate kappa h by solving some eigenvalue problem. So kappa h is computable. We can have concrete value. Given domain, we can set the function space, set up the function space, and then we can calculate the value of kappa h. And also we need some constant. This is about the average operator. So this for U, the average of U, the difference estimated by the gradient of U with some constant CTH. This constant is easy to obtained. So then the prior error estimation is given something like this. So left side is the energy error between U and projection U. And the right hand side, so we have kappa H and CH. So all the terms are computable. So we can have the explicit value CH in the prior error estimation. So here are some result. So this is the result for the prior error estimation for Stokes equation. So the domain is a big cube minus a small cube, and then we have a non-convex three-dimensional domain. And for you see, we subdivided the cube into small cubes, and then for each cube we have some tetrahedral element, and further we divide each tetrahedron into 4 sub-tetrahedron. So this is the idea of Zhang. So he proposed such kind of method to do the mesh generation. So and otherwise, if the mesh is not created in this form, then the matrix in the linear equation will be singular, and the computation will be not stable. So here some result. So you see, because it's a non-convex domain, we can see the order. So for k equal 2, so the Scott-Waterley FEM is constructed by piecewise polynomial of degree here 2 or 3. So the polynomial of degree 2 or 3. For degree 2, we have order like this, and k at 3 order like this, almost 1. This one, for k equals 3, it is stable computation. For k equals 2, so the matrix will be singular. Anyway, we can compute by using some efficient solver. Okay, so then the next subproblem is about eigenvalue problem of differential operator. So we need Poincaré constant in our estimation, in our proof. So let's consider 2 kinds of Poincaré constants. One is about you see just the scalar function u. Yes, u here. Okay, so for u belong to the H10 space. So we have Poincaré constant like this, and it is related to the eigenvalue problem of Laplacian. So this is eigenvalue problem. And also, because now we are considering the divergence-free function space, so we can also have the another kind of Poincaré constant, so C2. So for the odd function, so they are divergence-free. So you can see that so the eigenvalue problem something like this. So yes, something missing. Okay, like this. Okay. Okay, it's easy to see that the C1 give upper bound for C2. So we can evaluate the constant directly. So for example, here, so to bound the eigenvalue problem, so there's my recent result. So okay, I think the time not so very limited, so just some main result. So in this theorem, so we have projection from bigger space to FEM space, and some inequality that describe the relation between different norms. So left-hand side energy norm, right-hand side energy norm. So if constant CH is variable, then lower bound eigenvalue is given by a very simple formulation. So with approximate eigenvalue and also the quantity CH. So this result can be regarded as the extension of Markov result and also Gilbert's fix and also related result. You see some, for example, Kikuchi and Kobayashi, Carstensen, and also the idea. So I have to show thanks to Nakao because we had discussion on 2009. So there she introduced me some very important book that later I developed that kind of result. Let's consider the eigenvalue problem for the Poincaré content. So we can, for 3D case, we have quantity which we can give explicit value like this, a lower bound like this, okay? And then we can give a bound for the lower bound for the eigenvalue. This is for Laplace operator, and for Stokes operator, something like this. We can see that the constant have improved upper bound. So this is smaller than this one. That's slightly improved if we solve the Stokes eigenvalue problem directly. Here now I would like to show you some numerical result about the stationary solution verification to the Navier-Stokes equation. So by following the Nakao's method with Newton-Kantorovich theorem and with a priori error estimation. So the domain, this domain is just error-shift domain. So yes, and f is a special f. We select f like this, and epsilon a smaller value, small value like this. So we apply joint method to create the mesh, and for Scott Wojcicki FEM, we select degree as 2, and Roberts Thomas space degree as 1. So this is one example. So this is in the graph we can see the approximate solution. So in this error-shift domain, and the real number is about 1, so it's not so big. So just also just 1, because f is small. Also epsilon is 0.03, but f is itself has a small scale. Then the result, so the approximate solution is little number is just about 1. So here's the details about the quantity in the proof. So we have, you see, lambda 1, and the Poincaré content, and CH with kappa h, and CH. Here I think we need some square. Yes, and this value. And the K, so we need the bound of tau. And yes, and so this is just alpha omega equal to this quantity. So yeah, in the prediction of Nakao's method, so this inequality is very important. So there is one condition. So this kappa must be less than 1. So if it is bigger than 1, then the proof it will fail. Also, you see, we have some. Yes, then we can. For the moment, in this computation, for example, the eigenvalue problem or the kappa calculation are done just you see with classical numerical schemes. It's not a rigorous computation. So yes, the rounding error, yes, still remains in the result. So there we need to verify the eigenvalue problem, a matrix with dimension about 1 million, very large one. And if we consider the Rabia's result, so in this case, so the value of n like this, and condition in this theorem, now it is bigger than 1. It means for this theorem, it fails. But our computer-assisted proof works well. Yes. Okay, there's another example, just epsilon like this, and just result like this. So now you can see some vertex around here, and some quantities. Okay. Okay. At the final page, I would like to say the big challenge in verified computing. So there are very large scaled metrics that we need to solve. For 2 by 2 by 2, so subdivision, very raw mesh, there will be 160 elements. And the dimensional matrix is about 19,000. Very raw mesh, just 2 by 2, but the element and the dimension of space matrix are very big. For 4 by 4 by 4 subdivision, we will have matrix with dimension over 1 million. The reason large scale matrix include, you see, for Scott-Wageles FEM, so we need high order FEM, high order polynomial, D bigger than 3. And also to have stable computation, so we should do some re-subdivision of each element. So that is that's why we have 160 element. So for this very raw mesh. And also the Lagrange multiplier method applied to the divergence-free condition, we make size of matrix doubled, almost doubled. So here are some concrete results. So for divergence-free condition, so this is a set point formulation by using the Lagrange multiplier method. So to this condition, this equation that forces divergence to be 0. So for the matrix, so we have A like this. A0 is symmetric and positive definite submatrix. C and D correspond to the divergence-free condition. So in fact, dimension of divergence-free subspace is just about 2000 for 2 by 2 by 2 subdivision. But because here we apply the Lagrange multiplier method, so the unknown we have you see 18,000 unknowns, about 10 times of the dimension of the subspace itself. So yes, so you can see that the divergence-free condition cause some big difficulty and big problem. And also the matrix A is not positive definite and has a large condition number, about 10 to 8. The interval computation about tau gives very raw upper bound at tau about 10. So it is almost no useful. So here we have some idea. So because the divergence-free condition, we can introduce some scaling parameter alpha. So okay, here the graph. If we change alpha, then the condition number, you see, if alpha around 1, very big. But for the value about 50, very nice, very stable computation. Then we succeeded in the solution verification or verified computation. Very important. Yes. So yes, so the to-do problem, you see, verified solution over refined mesh. So we need parallel computing with high performance computers. And also another try is to consider the divergence-free space by calculating the null space of this divergence operator directly. If we succeeded, then the unknown can change it from 18,000 to 2,000. Yes, so we want to construct this null space directly. Yes. Then, okay, almost I finished my talk here. Just one more thing, very short thing. So about code sharing and online computing. You see, in my opinion, I believe that for computer-assisted proof and verified computation, it is very important to share the source code and let other people read the code and repeat the computation result. But unfortunately, you see, because the computing environment differs from each other and it's not easy to repeat the code from other people. So, so in my lab, so to solve this problem, so we set up an online computing environment based on virtual machine technology. So the domain is ganjin.online. So you can share the code at this site, and other people can repeat code with the same environment because it is based on virtual machine. So the other people will have the same environment as yours. So then they can repeat the code. And also the computing capacity, CPU memory, hard disk can be customized freely. The memory wide from 4 GB to 10 terabyte. Of course, it costs some money. Okay. So now I would like to finish my talk here. So basically, we applied the Newton-Kantorovich theorem and Nakao method. And also, recently I developed the priori error estimation and also the method to give bound for eigenvalue. So in the future, there's so many things to do and so many challenges. Okay, I hope many people can join me to go further. Okay.
Thank you very much, Xuefeng, for a very nice and impressive talk. Are there any questions or comments? You can either use the chat or just stop talking.
I would have a question or remark. Hello, Xuefeng. Here's Michael Blum. At the beginning, when you introduced the method, I think it was around page 27 or so, but I don't quite remember. You made that statement that to bound the inverse operator, we could go via eigenvalue bounds, but you thought that this is very complicated, and that's why you wanted to use Nakao's method. But I want to object that this eigenvalue problem is very complicated. So it is not so complicated. Actually, a student of mine, Jonathan Wunderlich, who is, by the way, also present today, did this via eigenvalue bounds. It involves a non-self-adjoint eigenvalue, you are right, but the eigenvalue problem to be solved is a self-adjoint one. And he did that very successfully. And so the eigenvalue bounds in his case are complicated, but because the domain is unbounded. So that comes in addition there. So he did that for an unbounded and non-convex domain. But it is still possible, and this is not so terrible to solve that eigenvalue problem. So this is an alternative, of course, to use Nakao's method as long as the domain is bounded. But it's not true to say that the other alternative to go via eigenvalue bounds is terribly complicated. That's not true.
Many thanks for your comment. Also, I know something not in detail. Okay, to consider the eigenvalue problem directly. I hope to have more detailed discussion with you. Okay.
Yeah, we can have that, of course.
We don't. Yeah, we should do it early.
Maybe we get email contact.
Yes, by Zoom online conference.
Yes.
I have a quick question about, this is Evelyn Sander, and I'm interested about your code sharing idea. What sort of startup time would there be for somebody else to put their code in such a repository?
You mean cost?
So you were suggesting that this was not just for your own code, but for other people?
You see this site, okay, here, I think you can see my screen, right?
Mm-hmm.
Okay, this is for not only for myself, but for all the people, you see academic for academic purpose. So now there are several projects. So Hypercircle, Stokes eigenvalue problem, and eigenvector estimation. And okay, people like you, okay, can use this system freely. And for the you see, 4 GB memory, it is free. If you want to use 10 terabyte terabyte memory, then maybe you need to pay some money. Basically, it is free. Okay. You can apply account here, and then you can upload your code. Okay, for example, this is my account. For example, you can create a new project and then you can upload your code. You can select. Okay, so everybody can use it freely.
But so is it available if your code is written in any sort of implementation, or is it only for specific types of implementations? Like if you were using a different type of package for doing computer-assisted proofs?
Yes, you see, in this system, I will release the image of the computing server. So you can request me, then I can add the package to the server, then we can make a bigger image, a powerful image, to include all the package you need to add to this image. And then later, so everybody can use package on this image or on the virtual machine. You can check the package list. And if you want new, I can add. If it is free, okay.
Thank you.
And Jonathan wanted to know what interval arithmetic libraries you're using for parallel computing?
Yeah, and also how does it handle rounding for different processors?
I need your advice, your help, and your cooperation. Yes, this is one of my big dream to build an online computing platform for all the people. Yes, it is not for profit. It is not to earn money. That's to build a new platform for us. We can share freely and compute online freely.
Yes, that sounds like a great plan. But there was a question by Jonathan Jacket, Xuefeng. There was a question, and maybe Jonathan, you can ask again.
Yeah, so I'm wondering how the parallel computation handles rounding for interval arithmetic with the different processors.
Okay, I'm sorry. Okay, yes, for the parallel computing, now on this server, on this counting system, there are some, for example, PET-C and yes, some library inside, and also you can start cluster. Not only one node, you can start cluster, and then you can do parallel computing. It's basically based on the Google server. Okay, there are some parallel computing. I don't know whether I answer your question or not.
That's good.
So, other questions or comments? Actually, I have. Yeah, go on.
No, please. I had already one, so you go first.
Okay, so in your solution in the L-shaped domain in 3D, it looked like the solution was kind of 2D-ish. No, was there really a three-dimensional flavor to it? You know, all of these, there were two kind of vortices, and it looked like, were they really 3D, these solutions, or they were maybe this one, for instance. Is it the third direction? Does it have really non-trivial dynamics?
Yes, this is using it had depths, but basically the shape does with only 2D shape on the Z direction. There are no too complex structure or solution for the moment.
Okay, so it's essentially a two-dimensional solution.
Yes, and also the mesh is very okay. This is just okay.
But you have directly boundary conditions, so it cannot just be a two-dimensional picture. Something must happen on the surfaces which are, so to say, in the line of the screen now, because there is directly boundary condition. So it cannot be really two-dimensional.
And also, when I draw this solution, I only draw the middle layer, not on the top, on the bottom layer. Yes.
And another question, so do you have possibilities to kind of exploit symmetries from the problems using the finite element? I mean, now I don't see, but in the previous one, it looked like they could have been symmetries in the other one. And yeah, this one. So it's not clear. So are there ways, say, that you can exploit symmetries with this setup? Would it be possible in your space to impose some symmetries or not? Because
you see, the F itself is not symmetric, so the solution is not symmetric.
Okay, so the solution, no, so F is not symmetric, I see.
First part and the second part, third part, 0. So the solution is not symmetric, I think.
But say if you chose a symmetric F, do you think that your setup would allow you easily to exploit that feature?
I can try.
That's always when you want to exploit the symmetries, then you might miss interesting solutions, which are not symmetric, which break the symmetry. So that's always has two sides to exploit symmetries.
Yes. And the last question, so you mentioned that, it's not yet a proof what you have because you need to use interval arithmetic and it's challenging. So right now the challenge comes from the size of the matrix. Is that correct?
Yes. So if the matrix is not constructed properly and it can fail because you see we need value around 1, but if the matrix is with a bad scaling, then the tau is very big, so then no useful information. We just fail. Yes, and also this is just for very raw mesh, and if you want to have some solution with complex structure, we need a refined mesh, and then the accumulation of rounding error will be very big. Yes.
So now, right now, the limitations are memories. It's not like computing time. It's memory.
Yes, and this computing, you see, just about you see less than 100 gigabyte, less than 100, about 60 gigabyte memory, and also this just for approximate solution, not for arithmetic.
So this solution is not proven, and the previous one either. There's just interval arithmetic lacking.
The previous one, this one.
Yeah, this one. This one is also. This is not verified with interval arithmetic. No.
I cannot catch your problem. Sorry.
So this, you mentioned that you did not implement interval arithmetic. So for this one, the full proof is not done yet.
Okay. Not yet. For the moment, I only succeeded in 2 by 2 by 2 mesh. I have one successful example, but the solution had very bad approximation. Yeah. Anyway, the proof it works. Yes.
Okay. Thank you.
I have one more detailed question on the hypercircle method. I think we discussed that already, but I forgot actually. So you need to solve the problem divergence P plus F equals 0, right? You have to solve that for P. And how do you do that in detail? So you want to have the P in your hand, right? So not just existence, but you want to compute it, the P.
Yes, yes. So basically, in the algorithm for each FH, so we have to find some pH. So we need
This
to
is approximation.
in fact, just for each FH, we have concrete pH.
So because you stay in the same finite element space, then you can do that precisely.
Yes. Just the finite dimension space, then we can
you can compute it.
Exactly, rigorously, yes.
And then how to continue to get P?
P, you see, given
how do you apply that when so you have approximation FH and you can compute the solution PH corresponding to FH, but you need finally you need a P which corresponds to the given F.
Yes, okay. For that question, it's something like this. So okay, something like this. Let me write here. So we consider FH and the difference between F minus FH. So this one is estimated by some theoretical analysis, not by computing.
Okay, so that depends on F, so to say, what you get out there.
So now F does belong to L2 space.
Yeah. Okay, but how to estimate that error depends on F.
Okay, it's something like this. So for F, we have solution U, and FH, we have exact solution U bar. We have estimation like this: gradient U minus the gradient U bar. This is less than C0 H. So F minus FH. Yes, you see, the U and U bar that exist in infinite dimensional space, and the difference between each other is bounded by quantity C0H and the difference between F and FH. And also, yeah, then almost done. And U bar minus the U bar H. This is less than some kappa H FH. If you take the square of the hand side terms and take summation, then you can find the result.
So I still don't get how to compute P.
P. So
in the hypercircle method, that this function P. That was my question.
So given FH, we find some pH. So this is
okay. That's fine. Yes. That's fine. But so you apply that. Do not apply that divergence P equal F. You don't want to solve that equation divergence P plus F equals 0, but you solve that only for the approximations. You only solve divergence PH plus FH equals 0. Is that right?
Yes, you said it.
Oh, okay. Okay, I understand. So you do that only on the approximate level, and then of course you can compute it concretely.
Yes, that's the point.
Yeah, thank you.
Okay, very good. Are there any?
I have one question.
Yes, a good question.
So, I think I'm interested in your idea to improve the verification result. So in the end part of your talk, so you mentioned you add some scaling parameter to the Navier-Stokes equation.
Yes, yes, basically for the projection operator. So because we want to develop some, okay, there it comes. Yes, yes, here.
My question is varying such a parameter. Where is changed in your verification conditions?
So if basically alpha, before the whole term, so there's a mistake. And also, if we add alpha here, then the matrix will change something like this.
Yeah.
So it's something like this, alpha. Yes. Then by scaling parameter alpha, the condition number A can be greatly improved. Improved means it can be smaller, and then the computation become very stable. And then in my computation result, so it succeeded to give the solution verification.
I understand. So maybe some the metrics become diagonalized.
Just you see.
I mean, yeah. Yes.
I don't know why. I don't know why. Maybe somebody in the field about this FEM space so can tell us why. If we introduce this alpha, we can have stable computation. So it works well, but for the moment, I don't know why. Yeah.
Okay. Okay. I see. Yeah. I think it's a kind of stabilization technique.
Can this alpha be regarded as some kind of penalty term, which is very usual?
So. I think so.
Yes, you can. Okay, this is a Lagrange multiplier method, and you can scale the parameter in that method.
When it's a penalty term, then it's quite usual in numerical mathematics that you can stabilize computations by penalty terms.
Yes, you see penalty term. Yes, you see for the Lagrange multiplier method, there is penalty term.
Yeah.
Okay. Thank you very much.
Okay. There any other questions? We've had quite a few, so if not, well, I'll wait maybe 10 more seconds, but it's already 11:16, and I assume it's pretty late right now in Japan. It is 15 past midnight. Yes. Okay. Okay. So, well, thank you very much once again, Xuefeng Liu, for giving us a very interesting advanced talk. So let me thank you once again. And let me finish by saying that next week we'll have Nili Manigam, and she will be speaking about the modification of Schiffer's conjecture and a proof via finite elements.